Okay, I want to talk about regression. Both simple and multiple. Simple regression and multiple regression. Now, and this is based on correlation. So one of the things, correlation will tell us things and it won't tell us things. It will tell us if there's a relationship, and again remember that that is both directional, either positive or negative, and it also has to do with strength, whether it's a strong correlation or not a strong correlation. Regression can be used to predict, but it is not indicative of causation. It doesn't mean it causes something to happen. Classic example is, if you make really good high school grades, you're probably going to make really good college grades. Probably. Positive correlation, pretty strong positive correlation. But making those good high school grades, that's not what causes you to make good college grades. So it doesn't cause it to happen necessarily. It might, but we don't know. We know it doesn't. In this case, we know you have to study and work. But anytime you get a strong correlation, it doesn't mean there's an effect there. Correlation is not causation, but it can be used to predict. If you make lousy high school grades, you're likely not to do very well in college if you get there. If you make really good high school grades and you go to college, you're more likely to do pretty well there too. So it can predict, and that's what regression is. Regression has to do with predicting. If you'll go back to chapter 6, and this is really chapter 7 stuff, but if you'll go back to some information in chapter 6, there it is. If you look at on page 142, remember the example we did last course? The first example of correlation we did is the relationship of sending cards to receiving cards. And we found out, well, the more you send, the more you get, the more you receive. So there's a positive correlation. So it is likely that the more you send, the more you get because of the positive, fairly strong positive correlation. We could use that likelihood to predict. If you tell me how many you send, I'm probably going to come up with some prediction to some, maybe a really good prediction or maybe not such a good prediction, some prediction of how much you're likely to receive. So, let's reproduce that data. Again, I'm on page 144. The table 6.4 is the data kind of in the middle to the left, where we've got sent and received. And let's do a scatter plot. And I'm going to let sent be my x-axis, or horizontal axis. I'm going to let receive be the vertical or the y-axis. And the numbers go from what? Sent go from 1 to 13. The others go from 6 all the way up to 14. So I'm going to just do it this way. And I got to go up to what? 18 for the received. So the first person, Doris, she sent 13, she received 14. So she sent this many, she received 14. So my dot is going to go right about here. So this one dot represents two things. How many she sent, 13, is above 13. How many she received, 14, so it's beside 14. So one dot equals two pieces of information because you've got two different number lines. And again, this is your old Algebra 1 high school graphing exercise. You've got an X and a Y number. We're plotting points. The next person was sent 9, received 18, so we're going to plot the point 9, 18. So 9, 18, about right here. The next person sent 7, received 12. Here's 7, here's 12. The next person sent 5 received 10, so 5 and 10's about here. And the other person sent 1 and received 6. So these kind of cluster, if I sort of just kind of draw a curve around the way those numbers kind of cluster, they start to take on a particular leaning. They lean from the lower left to the upper right, which we know, because you remember, because you wrote all this stuff down a minute ago, that is indicative of a positive correlation. And I explained that again using high school algebra 1, that a positive line slopes in that direction from the lower left to the upper right. So a positive correlation takes on that same kind of leaning. Now, it's positive correlation, but it's not a perfect correlation because it's not in a straight line. It's sort of like I could come up with a line that would be as close to most of them as possible, and we call that, we did define this last time, a line of regression. There's the word regression again. And you'll remember, humor me and act like you do, that the way we write down lines in Algebra 1 is according to a formula. There are a couple different forms of it, but the most common, the one that you'll at least act like you remember, is y equals mx plus b. That was just the other day for some of us, right? Y equals mx plus b. That's the equation of a line. The equation of our line of regression is very much along the same format. Now, what if someone sent 4? What would we expect them to receive? If someone sent 4, I go up to my line of regression, and I expect them to receive 9 or 10, kind of in the middle there. So we would predict receiving, say 9 or 10, if you sent 4. If someone sent 6, and nobody sent 6 in our data, if we sent 6, we would probably predict about, looks like about 11. So the question is, what's the equation that we could plug in one number and get out the other number? So that's what a line of regression is. Let's look at let's look at this more specifically. If you will look on page 158, you will see something called the least squares regression equation, which is just like the equation I wrote down, although they've changed the letters a little bit and labeled them just a little differently, but it's the exact same content. If I know what M and B are, let's say, for example, y equals 3x plus 2. If x equals 7, can I predict, can I tell what y is going to be? Can I calculate that? That's exactly what we're talking about. If you receive 7 letters, you're going to get back, if this is the right equation, that's probably not. But if my x is 7, my y is going to be 23. So our input is 7, our output is 23. X is the independent variable, Y is the dependent variable. You predict Y from X, or you use X to predict Y. That is, well, this, I just gave this the example of that equation. This isn't the exact equation, I just made this up. But since you asked that, hey, let's figure out what the equation really is. Since you asked. So, now if they calculate that for you, on on page 159, see that table 7.1? And they use all that, SS sub x, that means sum of squares for x, sum of squares for y, and they calculate an R value. Again, regression is based on correlation, R is correlation, and then they use that and spit out, in this case, they spit out the actual equation is the number received should be equal to 0.8 times the number sent plus 6.4. Remember that. 0.8 times the number sent plus 6.4. That's the answer. Now my question is, well, that's a lot of trouble to do it this way. Let's do it the easy way. How do we do it the easy way? Here's how we do it the easy way. Let's go to SPSS. Let's open up a blank document so I can put numbers in. And I've got two variables. I've got sent and I've got received. Let's make that capitalized. And I'm not going to do anything with the default options there. I'm just going to leave them as they are. So I've got sent and received. So again, remember you have to tell what your variables are under variable view. And as soon as I click data view, I'm going to see sent and received as column headings. So click data view, there's sent and received as column headings. So I'm going to put in the data just like it shows me on whatever page it was a second ago, page 142. So those are my sent numbers, here are my received numbers. Now notice these data have to remain paired because it's based on correlation, and correlation uses paired data. Now, if I'm going to analyze, where do you suppose I'll start? Let's go to Analyze. So you know this stuff already. So I'm going to go to Analyze. And then I'm going to do Regression, so I come down to Regression. Where is it? There it is. And I'm going to go over to Linear because we're talking about that line of regression, you remember? So I'm going to go to Linear. There it is. And it's going to ask me for my independent and dependent variables. And we said the independent variable is how many you send, and the dependent variable is how many you receive. So you don't want anything under statistics. I'm going to ask for R. I'll do that later. Never mind. I'll do that later too. Okay. If I click OK, I'm going to get an output window. Now, one thing that I get that I didn't ask for is the R value. R is 0.8. Look here under if I can make it right. Look at these numbers under this column. Unstandardized coefficients. The reason they're unstandardized is because we didn't do, in some of your exercises it'll tell you to get the standard scores. You remember those Z-scores? I didn't do that, so they're not standard scores. But I've got two numbers there, a constant and the cent coefficient. That means that my equation is going to be, to calculate received, it's going to be 0.8 times the cent, see those two right there? Plus, and my constant is 6.4. 6.4, that's, the constant is the number at the end that's just plus or minus something. In this case, it's a positive, so plus 6.4. Now, does that, hopefully this is a rhetorical question, does that equation look familiar? That's the exact same one the book calculated by hand. So that tells me if somebody sent, what was an example I used a minute ago, if somebody sent, let's say, 6 letters, then we would expect to receive .8 times 6 plus 6.4. Does that calculate to be 6.88? Does your slide rule say that? No. What is it then? Because I can do it wrong. Okay, I think that's right. So 0.8 times the number cent plus 6.4 would be how many we would predict that we're going to receive. And I think that's 6.4. So if we set 6, we're going to expect to receive about 7 back. On average, if you set if a bunch of people sent 6, they'd probably average about 6.88 we would expect. Now, we wouldn't necessarily receive 7 because it's not a perfect correlation. But that's our best guess as to how many we would receive back. That's our best prediction that we could make based on this. So you put your data in just like you do for a correlation. Matter of fact, you even get a correlation out of it. And I'm going to give you a sneak preview here. Look at those numbers, R and R squared. R is 0.8. That would be our correlation, which we calculated in another lifetime. But there's something meaningful about when you square R. 0.8 squared is 0.64. That has to do with a couple of things. In this context, it has to do with, that's how we calculate effect size. And we talked about effect size before. We'll do this a little more, but that's going to be something we're interested in too. Now, some other things we're interested in are these numbers, this number, and this number. Do those numbers look familiar because we get an ANOVA? So the way we report some of this stuff is according to our ANOVA data. We'll talk about that in a more specific example too later. But right now what I want you to come up with, I want you to be able to come up with this predicting equation. And one of your homework assignments is going to be to take numbers like this and come up with the equation out of it. And make a prediction with it too. If I were going to, see if I can remember to do this offhand. If I were going to do, let's get rid of this. If I were going to graph this, I would go to Graphs and Legacy Dialogues and click Scatter Plot. And label my X and Y axis accordingly. And again, we've done this before. But there's my scatter plot, which is exactly the graph I did by hand a minute ago. And there is a way, I'm going to have to refresh my memory. There is a way to add that line of regression, and offhand I'm drawing a blank on how to do that. I'll figure that out for you, though. It's something really simple, but I don't see where it is. Yes, graphs, legacy dialogues, scatter, or dot right here. That's how you do the scatter plot. I did choose simple, yes, the first one. The independent is X, the dependent is Y. Oops. How do I draw? Help me. I'm drawing a blank on how to get the line of regression. It's something really, really, really simple, and I can't remember it. Okay, anyway. Let's look at another example. Let's do a couple of other extra things, lest we forget how they work. If you look at exercise 33, data file 1. Exercise 33, data file 1. Oh, yeah, that's what it is. Oh, okay, here it is. Here's how you do this, the line of regression. If you double click on this, you'll get a box that comes up with these properties, and we want to look at element type, and we click fit line. There's my line of regression. Whew. Knew it was simple. Yeah, but where'd my dots go? This is the last one we just did. Yeah, but I don't like it. Well, I'll worry about that with the next example. Okay, turn to page, green cell can turn to page 275, lesson 33. If you look at the top of that page, you'll see where it says that the little Y hat symbol. Y hat equals B slope times X plus B constant. That's my Y equals MX plus B statement. Look at the scenario of the non-experimental study starting at the bottom of the page. Green and Salkin, yes, the other book. I've got different kinds. Let me get the data up here. Let's look at that. I've got 5 different kinds of strengths: quad strength, glute strength, abdominal strength, and so forth. I want to know how strength measures predict injury, and I've got 5 different kinds of strengths. Now, 5 different kinds of strength, that's more than one predictor, is it? So let's combine those into one predictor. How do we combine numbers together? Does anybody remember that from a couple of lifetimes ago? Let's say I just want to add these numbers. I think that's what it has to do, yeah. I just want to add these numbers together and let that be my overall strength measure. So for person number 1, I want to add 35 plus 27 plus 30 plus 11 plus 0 to get an overall strength measure for person number 1. Nobody remembers? Well, we make another column, yes. Yeah, I sum it somehow. Okay, I'm going to go to transform and compute variable. That's my first option. Follow along in your hymnals if you have them open so you can sing together. Compute variable. And I'm going to call this variable total strength. Now keep in mind that you can't use any spaces here, otherwise it'll yell at you and call you bad names. And I'm just going to calculate total strength by adding all these things together. So I'm going to say the quad score, and you move that over with a plus. The glute score, move that over, plus. Abdominal strength, move that over, plus. Arm strength, move that over, plus. And grip strength. So my total strength is going to be the sum of all the other strengths. So if you want to combine data, that's against the transform command. You don't put equal because equal is already there, see? Where I'm pointing? So the total strength equals the sum of all these together. So I've already got equals there. So when I click OK, I'm going to get another column of whatever the sum of those columns would be. So I'm going to click OK, and magically appearing, once it's going to give me an output window, which I'm going to close in a minute. I say OK, now everything's frozen again. Okay. What were you going to put where? Okay, my computer's hung up, but that's helpful. That's always helpful. Let's try it again. Oh, I can't even close the window. To start over. If you're watching the recording of this, yes, we are wasting unnecessarily wasting time, but I can't help it because trying again. Okay. All right, transform, compute variable, total strength is equal to this plus this plus this plus this plus this. Please work. Okay. And I believe it did. I don't want to save that output window. And sure enough, there I have a new column with total strength. So I want to use total strength as a predictor for an injury score. So to what extent does strength measure predict injury? So I'm going to go to Analyze, Regression, Linear Regression, And my independent variable is total strength. My dependent variable, we said, is injury. Is yours frozen too? So when I click OK, I should get an output window and give me the information that I can use for my equation. No, I want the total strength as the independent variable. I will say the numbers I'm going to get are not going to look exactly like your numbers in green and Salcombe because I did not standardize the scores. I don't see any reason to. Because we're going to see how a total strength score, you're right. A total strength score, you should have told me I did that. Okay. Okay. I'm going to see how total strength can be used to predict injury. That's what regression is. Well, yeah, we're not going to mess with that right now. So I'm going to click OK, and there's my output window. And the things I am interested in my output window are specifically the two numbers right here. So my dependent variable injury, see it says that right here, injury can be predicted by taking the total strength and multiplying it by the negative 0.615 and whatever that product is, adding it to 235.678. So I just use those two numbers. Injury is equal to negative, and I didn't have much room to write here. Let me see if I can do that a little better. Move that up a little bit. Not much. No, I can't. Actually, okay, I can't. So my coefficient, the coefficient means a number you multiply a variable by. That's why it says coefficient here. It's also why it's beside total strength. So negative 0.615 times the total strength plus 235.678, that will give a predicted injury score. Not necessarily what you're going to exactly get, but kind of your best guess. And again, the higher the correlation, the better predictor it is. But now keep it here. I told you I'd come back to this R squared thing. If you were looking green Salcombe back on page 277. It gives you, I'm trying to see if I can paraphrase anything better than they're doing here. By squaring R, that's my R squared, I'm looking at top page 278 now, we can obtain an index that directly tells us how well we can predict Y from X. And it talks about the percent of variance and stuff, which is, the bottom line is the higher the number is, the better predictor it is. Yes, well, R2 for that matter. The higher the R and R squared are, the better predictor you've got. Okay, now let me see if I can, the direct, Well, yeah, if you look at there are a couple of significance levels. Each of these, dang it, click. There it is. If I'm looking at my coefficient, and if you look at my significance levels here, for example, you'll see those are less than 0.05. So it's a reasonable predictor then. It's not just going to be kind of like a random number. If that was too big, you'd say, well, this isn't much of a predictor at all. Likewise up here, there it is. We'll talk about the APA write-up in a minute. And we'll report the levels of significance and degrees of freedom and everything. If you look at, okay, I'm skipping ahead because you asked me this question. If you look at the write-up example, the bottom of page 280, you'll see some examples of where the F of degrees of freedom, like 1 in 98. Here are my 1 in 98. Bottom of 280, see F of 1 in 98 degrees of freedom. And again, the numbers are different because we didn't standardize the scores. So you're not going to get the same numbers there. So that's why I wasn't going to tell you that unless you asked, and you did. So. They give you both. The first F of 1 in 98, that comes from the ANOVA. I should have standardized scores so it'd be the same. That comes from the ANOVA, degrees of frequency. F of 1 in 98 equals this F score. They got a slightly different F score. They got an F score of 11.59. I got an F score of 10.905. See where the difference is? Mine's better. And they tell you that P is less than 0.01. I would say P is equal to 0.001. Same thing, same level of significance. And then they also report, because there are only 2 of them, they also report the T-score. And that's the bottom. You see where they say T of 98 degrees of freedom? And they report a T-score of negative 3.40. I report a T-score of 8 point something. That's a lot different, again, because they standardize scores. But we still get a significant value for the p-value at the end of it. I'm going to give you a more specific write-up example when we do multiple in just a minute. Let's follow the directions very quickly for the scatter plot again. And here's where it lays it out better than I probably went through it too quickly a minute ago. Look on page 281. We go to graphs. See where it's got everything in dark highlights that you do. We go to graphs. We go to legacy dialogues. Oops, I'm going to get my ink off here again. Legacy dialogues. We're going to go to scatter or dot. And I'm going to go click simple and define. And my x-axis is going to be, in this case, total strength. That they give you a z something because they z'd it. I didn't. My y-axis is going to be injury. I click OK. Here's my scatter plot. Whenever it comes up. Okay, that doesn't look like much there, does it? But you never really know. It looks like it kind of goes down from left to right a little bit. Well, if you look at the next set, then this is what you're asking. Let me go double click on the chart. And click elements. Where's elements? Right here. And I want to click fit line and total. Yeah, fit line and total. And that is my line of regression superimposed on the scatter plot. step by steps on page 281. Allie, did yours? Are you running the same version? Oh, I don't know. I don't know. We might have a possible Mac issue here. Did you double click it? So is it in a different place? Okay. 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 So we're saying about it. If you do this on the Mac, it may be in a different place. Okay, on the very top bar, we're told. Okay. Yes, the question was when you get that elements box, do you just close that after you're finishing? Yes, and that should leave your graph with the line of regression on it. Yeah, it was a different box, yeah. And you can copy and paste from this into another document, like if you need this for a write-up or something. Is it the equation formula? Okay. I guess. I don't know. It's kind of like there's a formula in the middle. I don't have it in mind, but at least it sounds like it's the right formula. Okay, walk through me again. Again, the numbers are going to be different, but let me rewind a little bit because you got me ahead of myself. Look at the bottom of page 282 with the APA results section. A linear regression, I'm going to insult your intelligence by reading most of this to you. A linear regression analysis was conducted to evaluate the prediction of physical injury index from the overall strength index for elderly women. The scatter plot for two variables, indicates how they're linearly related, and the equation is, again, you give the equation right here. Predicted injury equals, and again, my numbers are slightly different because I didn't Z it. And then I report the 95% confidence interval for the slope, which is back on a little earlier on my output window. How do I get that? It is on page 282. Why am I not finding my confidence interval though? Because I didn't ask for it. I should have asked for the confidence interval. Okay. As hypothesized, elderly women who are stronger tended to have lower overall injury index. Well, that's because the line went down. And accuracy was moderate. The correlation was negative 0.32. My correlation was 0.316. Again, my numbers are different. And 11%, that's the R squared, 11% of the variance of the injury index was accounted for by its linear relationship with strength index. That's a fancy way of saying that that's how their variances are related. Remember, variance is the big thing. We talked about that in 7810. The variance in one is related to the variance in the other. The R squared gives you how related that variance is. And so that's why they say in such kind of high and mighty language there at the end of this APA write-up. So if you follow that and use this as a recipe out of a cookbook, you'll be fine. But the next thing, well, let me pause for a second. Let this sink in for just a second and ask what other questions you have. You're doing a good job of asking questions all along. Keep monitoring. I don't see questions from those of you playing the home version of the game right now. So far, okay, so far with this example? Because we'll do kind of okay. I will do one more thing. Okay, all we're doing, let me just recap very simply. All we're doing, we are generating an equation to predict. And that equation here is simply that injury can be predicted by, say, negative 0.615 times whatever the total strength score is, plus 235.678. So if I have a total strength score, I'm going to multiply it by negative 0.615, add 235.678, and that's going to be my predicted injury score.